QCD, which stands for quantum chromodynamics. And the strong nuclear force. So here's what we know. Okay, here's what we know. Okay, we know from experiments that protons / neutrons have a substructure of 3 tiny quantum particles called quarks. So in other words, if you look inside a proton / neutron, what you see here is that inside of this thing is we have 3 quarks. And I'll color them. Let's say one of them is red, one of them is green, one of them is blue. And what we say here is that the force that binds quarks together inside the nucleus, of course, is called the QCD force. So it's the QCD force. And what you really see here is that when I look at the QCD force, it's almost like it's spring-like. So you could imagine in your head that you might have little tiny springs that attach. And as you try to pull the quarks away, the spring snaps it back into place. Here's the important piece. Okay, so this is the important piece. The QCD force extends beyond the boundary of the proton / neutron. And so what do I mean by that? So when I look at the QCD force, and let's say that I have my proton neutron again. So if I look at that, here's what I see. I'm going to say that the yellow color this represents the QCD force. So when I come in here and I color it, you'll see that there's this yellow stuff, and this yellow stuff is binding the red, green, and blue corks inside of this thing. But it leaks out. So there's a little residual that goes beyond the border of the proton and neutron. So what I'm saying here is that this black line, that represents the boundary of the proton / neutron. And then what you're seeing here is that then there's this other piece right here, right? We're seeing this other piece. And this other piece here, you could see here that there is yellow that leaks out of the boundary. Okay, it leaks out. And so what we say here, that this leaking out is a residual force. And this residual force is called the strong nuclear force. And so the picture of this whole thing is that this is what we find here. So I'm saying that there's this residual force that really leaks beyond the boundary, and that's what we call the strong nuclear force. So for many years, or many years ago, no one knew about the quarks and the QCD force. And so what we found here is that what scientists or people thought was when you had a proton and a neutron. So imagine that here I have protons, and they're inside the nucleus, and here I have a neutron here, I have a neutron here, I have a neutron here, maybe I have a proton right here. What we found here is that when we looked at protons and neutrons, okay, so I'm going to imagine that this is my nucleus. So when we looked, was that, let me finish the sentence. What people thought was the strong nuclear force was all that was observed. And so when we looked at that, all we saw was this little residual force. Okay? All we saw was this little residual force. We didn't see inside of them. And so all of the physics that was developed way back then was that all we know is that this is the stuff, right? The residual force that binds protons and neutrons together. It wasn't till later on that people said like, oh, that's that's the cause of the strong nuclear force. So in summary, the QCD force binds quarks together inside of neutrons and protons, while the residual force, called the strong nuclear force, binds protons and neutrons together. In fact, even in today's language, people typically don't really separate QCD from the strong nuclear force. A lot of the times they'll say, oh yeah, it's the strong force, but they really mean QCD. So, but we all know that it's one and the same. So once again, the strong force is the residual force. It's the leftover of the QCD force, right? It's the leftover force. So now, here's what we know. The attractive so it's more common to not say strong nuclear force. It's common to say the strong force. So the attractive strong force binds, and here we go, protons / neutrons together. I know I already said that, but we need to repeat this. And here's the key thing: with exactly the same strength. With exactly the same strength. So now, here's what we say. Because they have exactly the same strength, what we come over here is, what this really tells us here is that the strong force does not distinguish between a proton or a neutron. Because of this, we now say this. We then say that a neutron, which is, and a proton, because they're treated exactly the same, neutrons and protons are now called nucleons because they're treated exactly the same. So if they're treated exactly the same, here's what we find. We have protons and neutrons. So we have a proton here, proton here. Let's say we have a proton here. So I have two protons, and then I have a neutron. Let me move this over a little bit more. A neutron. And so what you're seeing here is that what does the strong nuclear force do? It binds and surrounds protons and neutrons. So they interact with each other with an attractive force. And they bind and they have the exact same strong force, which is amazing when you think about that. So what does it do? It binds proton to proton. It binds proton to neutron. It binds neutron to neutron with exactly the same strength. So now we could ask the question again, and we ask the question up here of why doesn't the nucleus, why is the nucleus not blowing apart? So if we come up here and we go right here, because that's the question that started it all, our answer is this. Answer. The attractive strong force is much stronger than the repulsive electrical force. And what you find here, when I say much stronger, so on energy scales today, it's about 1,000 times stronger. 1,000 times, I said thousands. So it's 1,000 times stronger. So it's much stronger. As we get to heavier nuclei, you're going to see that that number diminishes. And so, okay. And so when I draw my picture of the nucleus, it looks something like this here. Here's my nucleus. I'm going to put in my protons. Right, here's my protons. So now if I come in and I put my neutrons, then my neutrons, maybe they look like this. When I look at the electrical repulsion is pushing very strongly outwards. It's trying to blow the nucleus apart. But at the same time, this nuclear binding then is stronger, so that the strong force is actually pushing down harder. So then the strong force is then greater than the electrical force.